Welcome. Today's Prelab covers the densities of liquids and solids, the so-called pycnometer lab. Now this is a technique-heavy lab, so I want to walk you through the reasoning before you get to the bench, not just the steps. Density is mass divided by volume. It's a simple formula, but notice what kind of property this is. It's an intensive property. So a paper clip made of aluminum and a cathedral built entirely out of aluminum would have exactly the same density. The amount doesn't matter. That's exactly what makes density useful for identification. Today, you'll hand back two numbers that name your unknowns, one for a liquid and one for a metal. Now here's the catch. Mass is easy to measure precisely. Volume is not. That tension is what this entire lab is built around. So why not just use a graduated cylinder? It's a reasonable question. Why not just pour the liquid into a graduated cylinder and read it? Well, let's look at the numbers. A 10 milliliter graduated cylinder reads to about plus or minus 1/100th of a milliliter. Now on a small sample, that's roughly 1 part in 1,000. Now compare that to the balance, which is plus or minus 0.0005 grams, or 5/10,000ths of a gram for a 30-gram sample. That's 1 part in 60,000. Now a quick note here. I'm assuming here that we are using balances which read to 4 decimal places. Now that's the case for all the balances in room S325. In other labs, we have balances which only read to 3 decimal places. So if you're carrying out the experiment in one of those rooms, you will have to adjust accordingly. The balance is dramatically more precise than any graduated cylinder you'll pick up. So the strategy for today is simple. Never measure a volume directly if you can weigh it instead. Every volume in this experiment comes from a mass and a known density. This whole lab rests on one idea, measuring by difference. Now you can't weigh water by itself. It has no shape of its own. So you weigh the container, then weigh the container plus water, and subtract. Mass of water equals mass of flask plus water minus mass of flask. You'll use this idea at least 5 times today. For water, for the unknown liquid, for the metal, and for the water surrounding the metal. It also works for volumes. Volume of the metal equals volume of the flask minus the volume of the water. Let that sink in for a few minutes. Now let's take a look at the pycnometer. Now this is the tool that makes all of this possible. It's a wide-mouthed flask with a flat-topped stopper drilled straight through the center. You fill it to 2 or 3 millimeters from the top, then push the stopper in while twisting very gently. It's essential that you do this gently because if the stopper is forced down too tightly, it may get jammed and is difficult to remove. The excess liquid is forced up and out through that hole. Whatever is left inside occupies exactly the same volume every single time you use that pycnometer. There's no meniscus to read, no estimated digit. The glass itself defines the volume. Now, a few practical rules for using the pycnometer correctly. If no liquid appears at the hole, it's not full. Pull the stopper, add a little more liquid, and reinsert. Then wipe the outside dry. A film of water on the glass weighs just as much as the water inside, and the balance can't tell the difference between the two. And always weigh it with the stopper on, and with your stopper specifically. They're ground to fit one individual flask and are not interchangeable. Now, pycnometers are very expensive, and they cost well over $100 each. These things are not cheap. So move them around in a beaker, keep them away from the bench edge and the sink. Please be very careful with these. So in part A, you're going to calibrate your flask. There are 6 steps here. Dry the pycnometer completely inside and out. Weigh it empty with the stopper and record every single digit on the display. Fill it with DI water to about 2 millimeters from the top. Insert the stopper with a gentle twist and confirm that water emerges from that hole. Wipe the outside dry with a paper towel and weigh again, recording every digit. Then measure the temperature of the water. One habit to build right now: analog rules do not apply to a digital balance. A display reading 34.1650 grams is 34.1650 grams. That's 6 significant figures. Don't round it and don't drop that trailing 0. So here's the chain of calculation for part A visually. 2 balance readings subtracted give you the mass of water. Divide by the density of water, and you get the volume of water. And because the flask was completely full, that volume of water is the volume of the flask. Let that sink in again. The volume of the water that you get here in part A is the volume of the flask. It's really worth pausing on. You calculate the volume of the pycnometer exactly once here in part A, and then you carry that same number forward into parts B and C. Don't recalculate it later, you reuse it. A common question at this point is, why do we bother with the thermometer? Well, water expands when it's warmed, so its density depends on temperature. You need this value for your room today, not just some fixed textbook number. You can see in this small table how much density shifts across just a few degrees. Use the full table in the appendix to find the value that matches your temperature. At 5 significant figures, that 4th decimal place is exactly why we're bothering to take a temperature reading at all. Another quick note: the density values in the appendix are actually reported to 6 figures, unlike the 5 you see here. However, in the advanced study assignment, the density is given to only 4 significant digits. So be sure to calculate accordingly. Now, part B introduces an unknown liquid, and it comes with a small safety requirement. We don't want any open flames anywhere in the room during this part. You'll want to wear gloves. If liquid contacts your skin, rinse with water, then wash. None of the liquids that we're using are particularly toxic, but you wouldn't want to leave them on your skin. Stopper the flask while it sits in a beaker, since the overflow has to land somewhere. Return the liquid to the container it came from when you're done, and place that container in the rack for used unknowns, so nothing can go down the drain. Then wipe the flask inside and out with a paper towel. Good news. Part B is short. There are only 5 steps. First, and I do mean first, record your unknown's number. A density with no label identifies nothing. Reweigh the empty dry flask with stopper. It should land very close to your part A value. And if it doesn't, the flask isn't actually dry. Fill it with the unknown, stopper it in a beaker, confirm any overflow, wipe it dry, and weigh. Get the mass of the liquid by difference. The volume is the flask volume you already found in part A. Density is, as we already saw, mass divided by volume. Now notice what you didn't do. You never measured the liquid's volume directly at all. You already measured that back in part A with water. Now let's look at part C, an unknown metal and a new problem. This is a pile of irregular metal pieces with gaps between them, and there's no formula for that shape. So instead of measuring the metal's volume directly, we let water take its shape for us. Volume of the flask equals volume of the metal plus volume of the water. We already know the flask's volume from part A. We get the volume of water by weighing the water that fits in around the metal. Subtract, and the metal's volume falls right out. This will take 3 weighings: the flask alone, the flask plus the metal, and finally the flask plus the metal plus the water altogether. So let's take a look at the full procedure here, step by step. Reweigh the empty stoppered flask and record all the digits. Record your metal sample's ID number. Add the metal until the flask is about half full, or until you've used the whole sample, and then weigh it, recording all digits. Add deionized water until it's completely full, and then insert the stopper. Then, and this step really matters, put your finger over the hole, invert the pycnometer, and then right the flask several times to drive out any trapped air. Top it off with water if any gets expelled in this process. Dry the outside, weigh, record all digits. Finally, remove the stopper and take the water's temperature. So here's the full calculation chain for part C. Mass of the metal, mass of the water, volume of the water, volume of the metal, and finally, density of the metal itself. The mass of the metal is the flask plus the metal minus the flask alone. The mass of the water is flask plus metal plus water minus flask plus metal. Volume of water comes from dividing that mass by the density of water. The volume of the metal is the flask volume minus the volume of the water. And the density of the metal is, as you would expect, mass divided by that volume. Now, I want to walk through one potential failure of this experiment in detail, because it's the single most common way to ruin part C, and that is a trapped air bubble or series of air bubbles. Now, follow the chain. If a bubble is trapped, less water will fit into the flask. That makes the mass of water too low, which makes the volume of water in turn too low. And because the volume of metal is the volume of the flask minus the volume of water, an artificially low water volume makes the metal's volume come out too high. And that finally makes the calculated density too low. Remember, whenever you increase a denominator, it makes the entire calculation too small. So be sure that you invert the flask several times and actually watch for bubbles coming out between the pieces. Sure, it costs you an extra 30 seconds, but it's worth every one of them. Now let's talk about cleanup. Cleanup has its own rules here for part C because there's a metal involved. You'll want to pour the water into a beaker first so that no metal ends up in the sink. Only then can that water go down the drain. Roll the metal around on a paper towel to dry it, return it to its jar, and put the open jar and its separate lid in the designated trays. Finally, return the pycnometer to me or your other instructor, not to the drawer. Wet metal returned to a jar will rust, and that ruins the sample for the next section and for any remaining classes that use those metal samples. Now here's one more significant figure trap which is worth pausing for. Every balance reading you take has 6 digits or 7 digits depending on the magnitude and depending on the mass in this experiment. But look what happens when you subtract two measurements that are close together. 119.827 minus 116.150 gives you 3.677 grams. So I started with 6 digits and another 6 digits, but when I carried out the calculation, I only got 4. A quick reminder, the balances that we're going to use will probably go to the 10,000ths place. But for right now, let's just assume that we're dealing with balances that go to 3 decimal places. The point will be the same. So subtracting two nearly equal numbers throws away significant figures. The decimal place itself is preserved. You still end in the thousands, but the leading digits cancel out. That single four significant figure value ends up limiting the precision of your final metal density. It's also exactly why we don't want the flask only a quarter full of metal. More metal in the flask means a smaller mass of water and a worse subtraction. Finally, let's look at the ways that this experiment could go wrong. First, water left in the flask before part B dilutes the unknown and it ruins the mass. A wet flask on the outside adds mass that isn't part of your actual sample. Air bubbles trapped in the metal. We just covered that one. Rounding the flask volume early and then reusing that rounded value 3 times compounds the error. Recording a density but forgetting the unknown's ID number makes the result useless. And reweighing without the stopper or with somebody else's stopper throws the whole calibration off. So if you remember one sentence from this whole pre-lab, make it this one. Weigh everything. Calculate every volume. A few closing notes. Do all the advanced study assignment calculations first. The report sheet follows the exact same steps in the exact same order, so working through the ASA sets you up for the report sheet directly. Show all your work in the spaces provided there. A bare number by itself earns partial credit at best. Both unknown ID numbers need to appear on your final report sheet. And the picnometer comes back to me or your instructor before you leave. That's the pre-lab. See you in class.